Now what is the concept or what is the omitted variable bias in multiple regression? Okay, what happens if you omit or if you are forget to include a variable? Okay, so when you have a variable which is omitted, okay, now you have like certain misspecifications. We'll see that misspecification. What are the misspecification? Okay, now one of the misspecification is that you omit a variable. Okay, when you include a multiple when you have a omitted variable in multiple regression, you have forgot to include a variable. Okay, as a result, what happens is your specification of the model or model specification is incomplete. Okay, so it is not the only way your model specification is incomplete. One of the way is you have omitted a variable, and because of that your specification is incomplete. Okay, that is the reason. Now we have a model may be incomplete in many of the cases. So let's try to see what is the model specification and where all it can be. Okay, so what are the model misspecification? Okay, so think about it. Okay, okay, model misspecification can take many of the forms. Okay, here in multiple regression we are not doing any time series analysis. Okay, we are only we are only interested in there is a dependent variable and there are multiple independent variables. Okay, now the model misspecification which we can see is, one is if we are misspecifying the functional form. Okay, that means either we are not including important variables, some of the important variables are not included. Okay, so that is a model misspecification. Okay, second is regression variable may need to be transformed. Okay, now what is this regression variable may need to be transformed? I think I took an example in the previous class wherein I said that there is a requirement wherein we need to take the wherein like we may be required to wherein we may be required to transform an independent variable. Okay, what was that case? Think about, you have y and x. Okay, and the y and x you have said that it's a straight line. In reality you are seeing this type of case. Okay, that means y and x are not linearly related. You are saying that it is kind of linearly related. Okay, that means that is a model misspecification, and the variable may need to be transformed. Okay, so if you model it, so you are trying to model it y equal to b0 plus b1x. Okay, if you model it like this, b0 plus b1 of, let's say, log of x, then it may be better. It may be better. Why? Because you will not see this type of error. Okay, so what you have is, when you are seeing this type of errors, okay, it means that the one thing is error terms are correlated. We have a issue. Remember, like last time we covered in detail like what are the various issues we can have. The issues we can have is error terms are correlated. We need to have them uncorrelated, okay, with themselves as well as with the independent variable. They should not be correlated with themselves as well as the independent variable. They can be related with themselves. That is a problem. So what we will see is, like in FRM, actually, like the multiple regression, they have not given they have not covered in detail with examples as to how that transformation can happen. Okay, we will, when we cover the time series, okay, which is a second part of our quantitative, which I'm not covering now, later. Okay, then we will see that, okay, how that model misspecification is an issue, and when we try to cover it with a time series, that kind of is taken care of. Okay, so here what you have is, okay, you have, let's say you are taking as x, maybe like ln x, maybe you could have taken e to the power of x or 2 to the power of x. It would have solved your problem. Okay, so regression variable may need to be transformed. So that is a functional form. Okay, data is pulled from different samples. Okay, so what you are having is, okay, rather than taking data for regression from the same sample, okay, what you are picking is you are picking some variable from here, you are taking some variable from here. As a result, the output that you will be getting from the regression equation would not be accurate. Okay, so that is a functional specification, misspecification. Another is time series misspecification. What is a time series misspecification? What we say is, think about, we can say that many times people do a regression analysis on sales. They will say sales for a period is dependent on sales of a previous period. So here what is happening is you are saying that this is my independent variable and this is dependent variable. Okay, but over here what is this? Okay, you are using this independent variable, but this independent variable is nothing but a lag thing of dependent variable. Okay, so you are including a dependent variable, lag dependent variable as independent variable. So you are saying that time sales in time t is a function of sales of time t minus 1, okay, plus b2x2 and other thing. Okay, so if you are using this, okay, it will result in errors. Okay, it will result in serially correlated errors. When you have serially correlated errors, what happens is your regression is not correct. So that's a violation of assumption of the regression, that correlation will not be there between the error terms. Okay, so that is a violation, and the way to do this type of analysis is not the multiple regression, but these are covered in your time series analysis. Okay, so that is why it is called as time series misspecification. Okay, another is including a function of dependent variable as independent variable. So you have some function, so you have, let's say, s or y equal to b0 plus b1x plus b2 some function of y you have included as independent variable. Okay, this is again a problem. Okay, because here what you are having is, here we are saying is a independent variable will be driving the dependent variable, but here independent variable is not. It is like a, what you have is, here also there is a relationship, and here what you may have is this. We are saying that these two variables are not correlated. Okay, here it may happen. Okay, so you are, if you are having a function of dependent variable as an independent variable, that is a problem. Okay, also sometimes you have independent variable that are measured with error. Okay, this typically, okay, I take an example of book value. Okay, now this, I know, like we are doing financial FRM, you would not have understood a book value. Book value is a concept. It is called as the difference between asset and liability. So book value is nothing but the worth of the company. So think about your all asset minus all your liabilities, whatever the difference, that is your worth. Okay, now typically the companies, they publish the balance sheet not on last day of the financial year. Okay, so whatever the last day of the financial year, the balance sheet does not get published on that. Balance sheet takes some 2 to 3 months to come to the people. Okay, now many times analysts, what they do is they try to find a regression using this ratio. This is your price to book. Price is the stock price, so P is the stock price and B is the book value. So P is the stock price and P is the book value, and here what they are saying is price to book value they will be measuring. However, what happens is this price is known with certainty, because I know the market price or the current market price or the market price on 31st March, I know. However, the book value I will not be able to know with certainty on 31st March. The book value of 31st March will be obtained only on, let's say, 30th of June. Okay, that means if you are using some value of book value on 31st March, it is not correct. It is with error. Okay, it is with error because you might be using some previous 31st December book value you are using with adjustment and finding out this. As a result, what happens is you are doing a time series misspecification. That is, the value that you are using over here is not the correct value. Okay, this is one example which I can think of wherein analysts typically they suffer from this issue, that is they will not be able to measure the things properly. Okay, so this is a time series misspecification. Okay. Then there can be other misspecification, time series for two or more different variable. Okay, so that let's focus on this because this is only what I wanted to cover. Okay, so important variables, transformation, lagged, function is dependent in the. Okay, so for you guys, like this is the only model misspecification that is required, others are not required. Okay, that is what this LOS has mentioned, that omitted variable bias in. So here we have to focus on the functional misspecification. Okay, now interpret a confidence sets for multiple coefficient. What is the confidence set? So it is nothing but the confidence interval. Okay, here why they have said a sets? Why they have said a set rather than interval? Because you have confidence interval for one variable, you have confidence interval of two variable. As a result, you have a collection of confidence interval, and that is the sets. Okay. So what you will be doing is, so remember what is the confidence interval for B naught. So you will be saying that B naught, whatever you have selected, plus minus T critical into standard error of B1. So that is a confidence interval for B naught. Similarly, it will be confidence interval of B1. It will be B1 plus minus standard. So it will be B naught. Sorry, it will be not. Here it will be standard error of B1. So here in this way you will be able to find out the confidence interval. So here you will be finding out the T critical. You will be finding out the standard error. Now the kind of questions that you will get in the linear regression, multiple linear regressions, okay, are more theoretical, as well as there will be problems wherein like you will have to compute all these values, like confidence interval you will have to do a F test, you will have to do a T test, you have to compute R square, you have to compute R square adjusted. Okay, they will give you some of the things and you will have to say okay whether there is some issue or not. Okay, so the idea is if you are very comfortable with single regression, okay, single regression, it is just you have taken to the multiple regression. Okay, it is you are not adding a lot of like you. It's not nothing like that is it's different. Only from a simple regression you are going to the multiple regression. So this is what you had in the regression. Okay. So in discrete probability distribution you have like actually if you see there are only two distributions that you have to cover, binomial and Poisson distribution. Okay, so if you are able to understand these two distribution, okay, Bernoulli is actually nothing but okay, it's a part of your binomial distribution. Okay, now what is a probability distribution? Before that, like what is a probability distribution? Okay, so my quick question is, normal distribution a probability distribution? Is normal distribution a probability distribution? Yes, right? Now this probability distribution has two types. One is discrete and another is continuous. So you have a discrete probability distribution and you have a continuous probability distribution. So this normal distribution is what type? Is it a discrete distribution or a continuous distribution? Okay. It's a continuous distribution wherein what we say is it's a density function rather than that. So here you will be having a density function and the area would be given as the probability. Okay. So for any distribution function what you need is, okay, you will be saying that okay it's a discrete, okay, or a normal or a continuous. Okay, so continuous distribution will be like this, whereas a discrete distribution, let's say we had covered an example of discrete distribution when we said about the throw of a die. When we covered the throw of a die, what we were having was we were having the values of x over here, and over here we were saying that x is 1, 2, 3, 4, 5 or 6. The value of the probability was 1 by 6. So when x is 1, the probability is 1 by 6. What if x is 1.5? What is the probability? What if x is 1.5? What is the probability? See that x does not exist for 1.5. It is 0. Okay. Over here you are getting the probability for some values, a discrete value. Okay. So think about a normal distribution which is existing from minus infinity to plus infinity. Okay. And you have a value over here 0, 1, 2, like that. If I ask you what is the probability that x will be equal to 1, what it will be? It will be 0, as we said, 1 point out of infinite point. Okay. So here in case of continuous distribution, we are worried about the area, and this area will give us the probability. Here we are worried about this because it is mapped with respect to the probability. Here area is the probability, here this y-axis is the probability, x is the number. Okay. Now probability distribution is the distribution of the random variable. Okay, and we will be getting some values. Okay. Same way, like we know the cumulative probability distribution, right? Cumulative probability distribution, if you want to plot it for this guy, how it will look like? You have x 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. You have 1 by 6. Okay. If you want to find out a cumulative distribution, okay, for x equal to 1, it is 1 by 6. X equal to 2, it is 2 by 6. So what will happen is this way. Okay. Others are 0, so it will rise this. So this way it will be increasing. So it is 1 by 6 from 1 to 2. At 2 it gets a jump. 2 to 3 it is 2 by 6. Get a jump. 3 by 6, 4 by 6, 5 by 6, and then it is 1 from there henceforth. Okay, so from 6th henceforth it is your 1. That is your cumulative distribution function. Okay. Now getting back, what is a Bernoulli distribution? So the question is, what is a Bernoulli distribution? Okay, Bernoulli distribution, it is like, think about you are tossing a coin. Okay, it is when you are tossing a coin, you will get either a head or a tail. Okay, so you are getting either a head or a tail. Okay, we denote, let's say, head as a success and tail as a failure. Okay, so in Bernoulli distribution, what we do is we only throw the coin once. Okay, so it is outcome of one experiment. Okay, so the number of trials in a Bernoulli distribution is 1. So the number of trials in Bernoulli distribution is 1. In this number of trials, sometimes you get success, sometimes you get failure. So what you have is you have the probability of success and you have the probability of failure. Okay. Now let's say if I give you, when the head comes, I give you 1 rupee, or let's say $1 is given. Let's say when the tail comes, I give you $0. Okay. However, this coin, okay, is not a fair coin. The coin that we are tossing is not a fair coin, and the probability of coming head is denoted as PH. The probability of tail is PT, or it can be also given as 1 minus PH. Either head or tail will come. So it's not a fair coin. Okay. The probability of head coming is PH. Okay. When head comes, you get $1. When tail comes, you get $0. What is the expected value? If I ask you the question, what is the expected value? What is the expected value of throw of coin? Okay. Or in other words, I am interested in finding out the expected value of this Bernoulli distribution. Okay. Expected value is the mean, right? So what is the mean that you will be having in this case? What is the mean here? Okay, why we can't determine? So you are getting a $1 with what? So if you see, you will get $1 with what probability? If let's say we draw a tree diagram over here, I am not saying this because this is not a fair coin. I am saying that this is not a fair coin. Probability of head is PH. So can I say the probability that you will get $1 is PH? The probability that you get $0 is 1 minus pH. What is the formula of expected value that we saw in earlier? We saw it was summation of pi xi. So summation of pi xi. So pH into $1, xi was $1 plus 1 minus pH into 0. So the expected value was pH. So expected value of one trial. So the Bernoulli, if somebody asks you what is the expected value of the Bernoulli expected value is over here pH, or if we say pH as the success, it is a probability of the success. So you have one trial, the probability of success, you have PS. So the success, this is the Bernoulli case, so you have success is PS. So the expected value is given as PS. Okay. Also, that is a valid for a fair coin. No, it is an unfair coin we have taken, right? So here the coin is unfair. We are not saying that probability of H is 50%. The probability of H is not 50%. It is anything. Let's say the probability of H is 0.2 or 0.3. Right? It is not a fair coin. Right? So we say that the expected value, assuming that you are getting $1, okay, it will be the value, expected value will be 0.3. Let's say probability of head is 0.3. This is not a fair coin. Okay. Now what we have over here, the probability, so the expected value of a Bernoulli distribution is PS. Okay. The variance of Bernoulli distribution is given as PS into 1 minus PS. Okay. Since you have PS, so this 1 minus PS is also called as Q. Okay. So you have the variance given as P into Q. For the Bernoulli, the variance is given as P into Q. Okay. So for Bernoulli, remember there is only one trial. Okay. The success is denoted as, probability of success is denoted as P. The probability of failure is denoted as Q. The expected value is given as P. The variance is given as P into 1 minus P or P into Q. This is the way we denote the variance. Okay. We have another distribution, okay, which is called as the binomial distribution. Okay. Now this binomial distribution is a special type of Bernoulli only. It's a special type of Bernoulli only. But here what we are doing is we are doing n times Bernoulli. Okay. So in a binomial distribution you have n trials. The trials, the number of trials that you are doing is n over here. Okay. So think about, you are tossing a coin. Okay. So you have tossed a coin. Okay. Coin can be can come as head or tail. Okay. But you are not tossing it once. You are tossing it n times. Okay. So you have to find out what is the probability that your number of head coming is k times. So I want to know what is the probability that head will come as k times, okay, where the probability of head is given as P, the probability of tail is given as Q. Okay, so you are throwing the coin n times. Out of that you are interested in knowing the head coming as k times. So this is written as NCK. So out of n times you want k times head will come. Okay, and if a head is coming 2 times, what we say is, let's say you are throwing 3 times. Okay, let's say you are throwing 3 times. It can come head head tail. It can come head tail head. Okay, it can come tail head head. Okay, now what is the probability of this guy? P head, probability of head coming is no, it will not be 1/3. Head coming is P, tail, and again head coming is P, tail coming is Q. So this is given as P square Q. What about this? Head coming is P, tail coming is Q, head coming is P. This is also P square Q. Tail head, tail coming is Q, head coming is P, this coming is P. So it is again p square q, qp square or p square q. So here what you have got is 3p square q. Okay, so this 2 is coming because you have head as 2 times. So what we write over here is p to the power k. The number of times head is coming, p to the power k. Q is coming 1 over here, or 1 has come as the total number of 3 times minus how many head time is coming, minus 2. So here q is to the power n minus k is being written. So what we say is, if you are throwing a coin, let's say not a pair coin, probability of head is p, probability of tail is q, the probability of tail is q, so the probability that head will come k time will be given as this. So this is the probability distribution for a binomial variable. So you have a binomial variable and the probability distribution for a binomial variable is given by this. So we will apply the same case over here. It is 3c2 p square q to the power 1. So 3c2 is 3 p square q. So this is the answer. So this is what we have found. Okay, so make sure that you know the binomial variable. It is given as nck p to the power k q to the power n minus k.